So in today's lesson, we're going to be learning about efficiency, energy sources, and energy conservation. So if we think about efficiency in everyday life, then typically we're looking at, making the most out of our time, or making the most out of what we have, and so on and so forth. So if we're talking about energy efficiency, we're looking at the same sort of idea, making the most out of the energy that we put in versus, and so we measure that by looking at how much energy is put in versus what we get out of it. And so when calculating percent efficiency, it's the same idea. So percent efficiency really just describes the useful energy output versus the energy input. And to get that as a percentage, of course, we're going to be multiplying by 100. So let's look at an example to make more sense out of this. So if we were to consider the incandescent light bulb, we know that we are inputting a certain amount of electrical energy. So that is our input. Okay, that's our electrical energy. And so let's say, for instance, I'm just making this value up. We input 100 joules of electrical energy. Now, in an ideal situation, that would translate into 100 joules of light energy. And of course, we know that incandescent light bulbs are horribly inefficient, and that really only out of the 100 joules of electrical energy input, we're likely to get about 5 joules of light energy as our output. And of course, the remaining energy, where the heck does that go? Well, we know that there's a whole lot of thermal energy that is output, but that is not useful energy, and so we don't really count that as useful energy output when determining efficiency. So let's look at this as an equation. So if we are looking at the percent efficiency, then we would look at our output, and so the useful energy output, not just the whole energy output, because of course energy in the universe is always conserved, and we would always get 100% energy output based on our input. But in this case, we're only looking at our useful energy output, and in this case, that was our 5 joules of light energy, compared to our 100 joules of electrical energy input times 100, and that is where we would get the 5% from. All right, so let's look at a second example. So I want to be able to pull up, I'm just going to pull up a video here in our browser, because what I have there on the right is an internal combustion engine. And I want to pull up something that has a bit of an animation to it so we can see that. So internal combustion engine. I want an image of that. Let me see, where is a nice image? Let me type in GIF. Oh, there we go. This one looks good. All right, so let's take a look at this GIF here. So this is an internal combustion engine, sort of like what you would have in a vehicle. And so you can see just over here is where my fuel, my gasoline, is going to be input into the engine. So it goes into this combustion chamber over here, and you can see that it's getting ignited. And of course, when a fuel gets ignited, it's going to produce some carbon dioxide and some water vapor, and also going to be taking all of the energy, all the chemical potential energy, and converting it into a different form. And so that combustion is going to produce a lot of pressure, and that pressure is going to push down on this thing called a piston. And the piston moves down, and that's going to move my motor. So afterwards, what happens, you can see once the fuel is injected into the combustion chamber, then it moves upward, and that gives time for the ignition to happen. Okay, combustion occurs, and then this valve here over here on the right ends up opening, and that allows for any gases that are produced to be exhausted out the exhaust. And so that happens over and over and over again. So let's take a look at what our energy input is. So in this case, the energy input is coming from the gasoline. And so what is the actual energy form? Well, it's chemical potential energy. Oops. So chemical potential energy. And then, so let's take a look at, well, what is the useful, not just energy output, but the useful energy output in this case? Well, hopefully you're getting that there's that mechanical energy. That's going to move that motor and help your car to run. Now, of course, if we were looking at the entire process, right, that 10% is really just the mechanical energy that is the useful energy. You know, our percent efficiency is describing the amount of mechanical energy that is useful as a function of the total input, which is our chemical potential energy. But somebody might say, well, where the heck does the rest of the energy go? Well, of course, in an internal combustion engine, like the rest of the energy is largely going towards thermal energy. So thermal energy and just the general heat of those exhaust gases. You have your coolant in there, and that's going to absorb some of the thermal energy as well. Also, you know, it's not a silent process, so there's some sound energy. So some of the energy is going to be lost as sound. All of that contributing to the overall energy in that transformation. All right, so take a minute to write this example down, and then we'll get started solving it. So let's read through it. A family uses several planks to slide a 350 kilogram piano onto the back of a pickup truck. Okay, so let's just kind of look at that scenario. So I would have a ramp of some description that I've got my piano, and I'm going to use that to get the piano onto the back of some kind of truck here. And so people are going to apply a force to get that upward onto the position onto the back of the truck. So the box on the back of the truck is 81 centimeters above the ground, and the planks are 3 meters long. So I've got the distance here of my plank, which is 3 meters, and I also have the height of this truck here as 81 centimeters, so in other words 0.81 meters. All right, so let's think about what work was done in loading the piano. So work, of course, is equal to my force, the applied force, times my displacement. And it says that there was an applied force of 1,500 newtons. That's what I used. That's the force that I applied over that length of the plank, which was 3 meters. And so overall, that will give me 4,500 joules of work that was done in loading the piano. And really, what is that? Well, that is the work that I put into it. That's my input. Okay, that's how much energy I put into it. And now, well, what did I actually achieve by doing that? What was the useful energy output? Well, my goal was to get my piano from the ground into the back of the truck. That was my goal. And so what did I achieve out of this? Well, really, I just achieved work against gravity, right? I increased the gravitational potential energy of that piano by moving it upwards. So the useful energy was just the work that I did against gravity. That was the energy output. I just got it raised to a higher level. And so use to figure out the amount of energy that was output that was useful in this situation, I'm going to use my equation for calculating the gravitational potential energy. So the mass of my piano was 350 kilograms. The gravitational field strength was 9.8 newtons per kilogram, or meters per second squared if I want, over a distance of 0.81 meters. Sorry for squeezing that in. So when I push all those numbers into my calculator, I end up getting to two significant digits. 2,800, oopsies, let's make that look like an 100 joules. And so that's what I get out of this situation. This is what I've accomplished. Now, of course, I'm going to take that value as I input it. I'm going to keep that in my calculator unrounded. Another way that I could do this is just to carry a couple of extra sig figs in this situation. So finally, I want to calculate the efficiency. How efficient was this process? Now, even though it would have been really difficult to lift this piano directly, the use of the plank helps me to sort of manage that, that energy and distribute it over a longer period of time, or a longer distance rather, and that allows me to manage this task a little bit more easily, but it's not as efficient as it could be. So let's calculate my efficiency. Percent efficiency is equal to my useful energy output divided by my input times 100. And so if I look at that and I input my values, I'm going to say, well, that was my 2,800 of useful energy divided by my 4,500 joules of energy that I input. Typing that, I'm going to keep my unrounded value for output energy, divide that by the 4,500 joules, and that gives me about 62%. It's not too bad, really, 62%. Where did the rest of the energy go? Well, instinctively, people will say friction. But guess what, people? Friction is not a form of energy. The form of energy that is, is wasted energy in this situation largely is thermal energy. Now, how does the thermal energy get created? Well, that's where we say, well, friction over a distance will create my thermal energy, right? The work that friction does produces thermal energy. All right, so we've done a lot here today. Now I've got some questions for you to practice, because some of this is kind of counterintuitive a little bit, I think. So I'm going to strongly suggest that you take some time to work on these homework questions, these practice questions. Ultimately, though, I do have a task for you to complete. I want you to take a look at Table 1 on page 254 of your textbook. Let me see if I can pull that up as a web browser. What you're going to do, let me see if I can do that right away. I'm going to go to My Nelson. Just to show you this in your textbook. And what you're going to do is you're going to see there's a table. And in that table, try that again. Success. In this table, what you'll see are the efficiencies of some various energy transformations. And I think it's kind of interesting. So I'm going to shift over here to this table. So here's the table that I'm talking about on page 254 or 244 rather. So you're going to take a look at this table and just read through some of the info that you'll see there. And I'd like you to write a half-page summary for me to explain which energy transformation efficiencies, not the, energy transformations themselves, but the efficiencies were surprising to you. And in what way were they surprising to you? And be descriptive. This is a 5-mark assignment that I'm assigning you in communication. So provide some detail to thoroughly explain to me what it is about these particular efficiencies that were surprising. And for instance, you don't have to list one particular efficiency. Maybe there are a few of them that surprised you, and that will give you a lot to talk about. Whether the efficiencies were particularly low, whether they were particularly high, maybe some were sort of in the middle and you expected them to be higher or lower, whatever. Anyway, that is your task for the rest of the period, aside from the questions to do. So whatever you're in the mood for today, nearing the end of the day on a Friday, whatever you feel like doing, that would be great.